On the left hand side, this is a case of a log. You have x on the denominator, x to the power 1 on the denominator. The numerator is a number. That's clearly a log. But on the right hand side, this is why this question is hard. It's the second term, the second integrand. If you have a look right here, guys, oh, I've got the dx as well. If you have a look right here, how would you be able to anti-diff this? If the first thing that might pop up is simple sub, maybe you've got one function divided by another function. The problem with simple sub over here is if you let u equals to the denominator and you derive it, you get 2x plus 1, right? So deriving x squared plus x plus 1, you get 2x plus 1, but 2x plus 1 does not eliminate 2x plus 4. You've got this 4, that's not a plus 1, so it's a bit sticky, you can't eliminate just yet. But the clever thing is, why not change this 2x plus 1, 2x plus 4 into a 2x plus 1, right? If you have a 2x plus 1, you can definitely anti-derive this. So here's what you can do, guys. This is the smart thing about this question. 2, so I'm rewriting this again, right? And then for this function right here, negative half, you can write it as 2x plus 1 and then plus 3, because 2x plus 1 plus 3, that's the same as 2x plus 4, right? And what you can do is, okay, you can split your integrand once more. So 0, negative half, yep, I'm just rewriting this again, the logs. Right, you can split this part into two separate integrands. Which two integrands? So it's 0, negative half. Right, 2x plus 1, you can split it over here, 2x plus 1, x squared plus x plus 1. Right, once you have this form, you can definitely anti-diff this, right? It's substitution. You let u equals this, and then there we go. We did it before. You get the 2x plus 1 that can cancel out. And then dx, and then you can take the 3 out entirely, okay? So what that 3, just be careful. When you have this 3 right here, it's separate integrand. You have to go 0, negative half with the negative in front, because that negative applies to both terms, okay? So that's 3 over x squared plus x plus 1 dx, right? Okay, so yes, you actually do get 3 separate integrands, and the working out is going to be long, but once you get up until this step, guys, there's only one more one more trick to this question, and then you can definitely solve for it. So let's have a look over here. What can we do? Left hand side logs, that's fine. Second part, that's just your simple sub. And then the third one, what can we do on the third term? Now that presents another problem. What you have is a constant on top and you have an x squared on the denominator. If you think about all the techniques that we've learned, the one that strikes out is the tan inverse, right? If I derive tan inverse, I get a on x squared plus a squared. That is a constant on top, and then there's x squared on the denominator. We have something very similar here. Constant on top, x squared on the denominator. The only problem once again is there's an x here. There's no x on your tan inverse, right? But you can manipulate things so that it actually looks like this, okay? So this is what I'll do. I will keep the integrand, so for the sake of working out, I'll keep everything the same first, okay? Minus 0, negative half, 2x plus 1 over x squared plus x plus 1 dx. Right, what you can do here is you can manipulate things. So 0, negative half. So another way of writing x squared plus x plus 1, you can complete the square so that it looks in something that might look like a tan inverse, right? So complete the square, you halve the coefficient on the second term in that case. So I'll do it on the side quickly. X squared plus x plus 1. If you halve the coefficient, you get x squared plus x plus half. And then you square the coefficient and then you minus it back and then plus 1, right? So in that case, you get x plus half square. Minus half square is minus 1 on 4. Minus 1 on 4 plus 1 is plus 3 on 4. So you can actually write this as x plus half square plus 3 on 4. And then of course, you can take the 3 out and then everything's over 1 and then dx. Right, now this is starting to look like your tan inverse, right? Doesn't it? Right here. You've got your a, which is the 1, or kind of 1. You've got basically a constant on top. We can change that later on. You've got the x square, which is over here, x plus half square. See, that square, that's, you can let u equals to x plus half, and then that becomes your x square, or u square. And then of course, 3 on 4, a square, that's a constant, so that's fine. So yes, you can manipulate things to make it look like a tan inverse, and this is how you do it. Right, Guys, let's start anti-diffing one by one. Ignore the first one. This one becomes a log. Let's handle the substitution first. Let u equals to x squared plus x plus 1 du dx equals to 2x plus 1. Yes, that 2x plus 1 is going to cancel out, which is good. That's what we want. Dx is now du over 2x plus 1. Make sure you're changing things to u, so therefore your upper and lower terminals also must change to u. So when x equals to 0, u is equals to 0 squared plus 0 plus 1, u equals to 1. And of course, when x equals to negative half, we sub in negative half over here. Negative half squared is 1 on 4. 1 on 4 minus half plus 1. So 1 on 4 minus half plus 1. Well, minus half plus 1 is half. Half plus 1 on 4 is 3 on 4. Okay, and then you can start writing your integrand once again. I'll do the same substitution here first. Same thing here. So instead of let u, because you already let u equals x squared plus x plus 1, let's try a different one. Let v equals to x plus half, right? You want to turn this into a v squared. So that's in this form. So let v equals x plus half. Therefore, dv dx is 1. And the x equals to simply dv. Okay, once again, if you change your dx into a dv, you have to change your terminals as well. So when x equals to 0, v is equals to 0 plus half, so that's half. And when x is equals to negative half, v is equals to negative half plus half, that is 0. Okay, yes, this is a long question, but it's worth it at the end. This can easily be an exam question, guys. So make sure you know how to do this. Let's write your integrand once again with its new form. So the one on the left, that's fine. You can just keep it the same. This one just becomes a log. The one on the right, your new integrand, replace your upper and lower terminal with the u. So that's 1, 3 on 4. Now the 2x plus 1 is 2x plus 1. We leave it there. But then the x squared plus x plus 1, you can write this as u because we made it equals to u. And the dx is now du over 2x plus 1. And then happy days, 2x plus 1 cancels out. I'll keep writing over here so that you can see, so that the third term as well. Substitute half in, substitute 0 in for the v, and then it's 1 over v squared plus 3 on 4. Dx is now dv, so there we go. Okay, you can start anti-deriving. Just one thing before that. Let's cancel out, make things look nice. 2x plus 1 cancels out, and the 1 over here isn't quite right just yet. 1 over v squared plus 3 over 4. If you look at the tan inverse, when you derive that, it is a over x squared plus a squared. We know a squared is 3 on 4, so what's the equivalent of a? A would be the square root of this, right? So square root of 3 on 4. So what we want over here is actually a square root of 3 on 2. Because if you square root 3 on 4, then you get root 3 on 2. But this is a number 1. You want to change the 1 to root 3 on 2. What you can do is you can multiply this by 2 on root 3, right? 2 on root 3 multiplied by root 3 on 2, that's the same. That will become 1. And the clever thing is you can take the 2 root 3 out. You can take it out over here, right? And then you end up with root 3 on 2 over v squared plus 3 on 4. But the 2 root 3 comes out. And yes, you can actually start anti-deriving. Yes, so I'll write this one last one. Yes, I know this log is just stuck there forever. I feel bad for him, but we just have to keep going. We have to make things look nice to prevent the silly mistakes. It's important you don't make any silly mistakes. All this hard work with one silly mistake, lose a mark, that's just too sad, okay? So we take the 2 root 3 out. That is 6 over root 3, or simply 3 times 2 root 3 is the same as 3 multiplied by 2 root 3 over 3. I'm going to rationalize the 3 up top. The 3 disappears and you end up with 2 root 3. So I'll just write 2 root 3 and then the half 0 with the root 3 on 2 as the a, and then the v squared plus 3 on 4. That's the a squared, and then there we go. We can finally start anti-deriving this. Okay, I'll give some more space. So move it over to the left and let's have a look.